Hello and welcome to the 14th session of the Introductory Biostatistics Distance Learning course. Today we're going to be using stata to investigate how to do nonparametric statistical analyses, what we learned about in the previous lecture. So just thinking about how we can get it done using stata. So unfortunately I've been trying to stay consistent and use the SEPO data set for all of the Stadia tutorials, but in this particular case we're going to have to use a different data set because the SEPO data set really didn't have any matched pairs, which is what we want to be able to conduct the Wilcoxon signed rank test. Okay, so just like we did in lecture, we're going to start with the Wilcoxon signed rank test, as I mentioned. And so since we're working with a new data set, which I've already loaded into stata, the reason you can tell is if you go over here to the variables window, this doesn't look like the familiar variables that we had in the SEPO data set, but instead we have 4 variables: pair, patient, control, and difference. So when you're working with a new data set, it's always a good idea to take a look at the data so you know what you're working with. So if I go up here to the data editor, which allows me to browse the data, I can click on that, and so you'll see we have 10 different pairs. So this is a matched study. This is why we couldn't use the SEPO data set, because there were no matched pairs in the SEPO data set. So there are 10 pairs. The patient here refers to a patient with multiple sclerosis, as we saw from the example in lecture. The control here refers to a matched, I think it was matched on age and gender, and maybe one other factor. So control refers to a matched healthy control. Okay, so the patient is someone with MS, and the control is a matched age and gender matched healthy control without MS. Okay. And so what we're measuring here is a continuous measure of an MRI outcome. So here's the number in the patient, here's the number in the control, and here's the corresponding difference between them. Okay? All right. So, so since we have a very small data set, only 10 pairs, we're unwilling to assume that the differences have an underlying normal distribution. I'm not going to produce the histogram here, but in lecture we took a look at the histogram and it didn't look normal. So we have a very small data set. Normality doesn't look like it's justified, and as a result we've decided we want to use a non-parametric test instead. You'll remember that in this sort of situation, a matched design, we could use a paired t-test, but again, we're unwilling to assume normality, so we're going to proceed with a non-parametric test. And specifically, we're going to use the Wilcoxon signed rank test. Okay? So before we proceed any further, you'll remember we've been using these 7 different steps for hypothesis testing. We can conduct the first 3 steps of those without stata. Remember, the first step is to state the null and alternative hypotheses, and since we've decided to proceed with a non-parametric test, the null hypothesis is always in terms of the median difference. Remember before, when we were working with t-tests and ANOVA and so on, these parametric tests, our null hypotheses always involved the mean. But now, when we're working with non-parametric tests, our null hypothesis here with the Wilcoxon signed rank test is that the median difference, patient minus control, is equal to 0. And then, of course, the alternative hypothesis is that the median difference, patient minus control, is not equal to 0. Okay, so that's our first step out of our 7 steps of hypothesis testing. And then in the second step, we want to state the type of data that we're working with. Well, here we have a continuous outcome and a dependent sample. Okay, a dependent as opposed to independent. This is a dependent sample because there are matched pairs. Okay, so we have a continuous outcome and a dependent sample. And so in the third step of our hypothesis testing, we need to determine the appropriate statistical test to use. and it turns out in this case we're going to use the Wilcoxon signed rank test. Okay? Alright, so I'm just going to close the data editor here. Now that I know what my data look like, I have 10 pairs of patients, one with MS, one without, a matched control. So in order to carry this Wilcoxon signed rank test out, I can use the sign rank command. Okay? There are two different ways we can complete this. We'll show them both. So in the first way, it requires that we've already calculated the difference between the matched pairs. And you'll remember in this particular data set, the difference is already here. It's this fourth column. Okay, so since I've already calculated the differences, I can type in the command sign rank, no space in between those words, sign rank diff equals 0, right? That's my null hypothesis, that the median difference is equal to 0, and I'll hit enter. Okay, and stata gives me this really nice output, so let's take a look at the output and see what we can gather from it. Okay, so if you look at the top, you'll notice this table which tells us about the positive and negative signs and so on. So remember, it looks at which of the differences are positive here, and then which of the differences are negative here. Turns out 8 out of the 10 had positive differences, and 2 out of 10 had negative differences. Okay? And so we had said that our test statistic is the sum of the positive ranks, right? And so here in this example, the sum of the positive ranks is 50, while the sum of the negative ranks is 5. And you remember under the null hypothesis, where the median difference is equal to 0, the sum of the ranks for positive and negative differences should be the same, namely 27.5 in this example. So again, just to make it concrete, I can look at my data set, and in this difference column, you'll notice that only 2 out of the 10 differences are negative. This one here, the second one, as well as the last one down here, the 10th one. Okay, so that's why we have this number 8 in the positive and the number 2 in the negative sign rows. Okay, so we note that the sum of the positive ranks is higher than expected because 50 is much larger than 27.5, which is our expected sum of positive ranks. Okay, so this tells us the direction of the difference. Namely, it appears that since we're taking patients minus controls, it appears that patients have a higher outcome measure. People with MS have a higher outcome measure than their corresponding matched healthy controls. Okay. So moving along in the output, we can next look here, which is the adjusted variance. Remember, we presented the formula for calculating the variance. Luckily, stata takes care of all that for us. And so that's the variance that it's using, 96.25. And then finally, at the bottom here, is our two-sided p-value. The reason I knew that was two-sided is because it says the absolute value of z, and it turns out the p-value is 0.0218. Okay, so now that we have this key information from stata, we can complete the remaining steps of our 7 steps of hypothesis testing. Okay, so remember in step 4, we want to state the summary statistic if possible, and so the summary statistic of interest for a Wilcoxon signed rank test is the sum of the positive ranks. So it turns out here the sum of the positive ranks is 50. Again, we said it was much larger than expected because we would have expected 27.5. So that's our summary statistic, the 50, the sum of the positive ranks. And then from there, in step 5 of our hypothesis testing, we state the p-value, which was down here in this step, 0.0218. And then based on that p-value in the 6th step, we decide whether to reject or fail to reject the null hypothesis. So hopefully, as you're following along, with a p-value of 0.0218, which is less than 0.05, we decide to reject the null hypothesis, okay? So we've decided to reject. That means that we do not think that the median difference between patients, MS patients, and matched healthy controls is equal to 0. We do not think that the median difference is equal to 0. Namely, based on our sample, we think that patients with multiple sclerosis have higher MRI measure compared to healthy controls. And the reason I knew it was higher is because there were more positive ranks, and the way we're calculating the differences here is that we're taking the MS patient minus the healthy control. Okay, good. So that was one way that we could have completed the Wilcoxon signed rank test for this example. This required that we had already calculated the difference and had that as one of our variables in our data set. What if we hadn't calculated the difference? What do I mean by that? Suppose this fourth column that I've highlighted here wasn't there. Instead, we had the pair and the patient and the controls outcomes, but we hadn't calculated the difference. How could we carry out the Wilcoxon signed rank test? Well, we would just type in the same command as before, sign rank, no space in between, but now we would type in patient, which is the name of the variable that contains the outcome measure for those with MS, equals control, which is the outcome measure for the healthy controls. And if I hit enter, you'll see I get the exact same output that I got above using the difference, okay? So just two different approaches for doing the same thing. One requires that you've already calculated the difference between matched pairs, and the other just requires the outcome in the two different groups. Okay, good. And then, just like we always do, well, how would we know the sign rank command if we were just starting out in stata? We wouldn't, so we would instead be using the drop-down menus. And so to use the drop-down menus to carry out this particular nonparametric test, we would go to Statistics up here, Summaries, Tables, and Tests, and then there's this choice, Nonparametric Test of Hypotheses, and then we would choose the Wilcoxon Matched Pairs Signed Rank Test. Okay, so Statistics, Summaries, Tables, and Tests, Nonparametric Tests of Hypotheses, and then finally the Wilcoxon Matched Pairs Sign Rank Test. And if I click on that, I get this little menu that says variable equals expression. Okay, so the variable that I'm interested in, if I use the drop-down menu, is the difference, remember? And I'm wondering whether the median difference is equal to 0. So on the left-hand side, I put diff for the variable that contains the difference, and on the right-hand side of the equal sign, I want to know whether the median difference is equal to 0 or not. Okay, and then I'll hit OK, and you'll see again, this is a third way that I've gotten the exact same output. Okay, all right, good. So that is the Wilcoxon Matched Pairs Sign Rank Test and how to carry it out using stata. So next, we want to explore the Wilcoxon Rank-Sum test. So I'm just going to go over here and load a different data set for the rank-sum. I'll share these data sets with you. Okay, so now I've loaded the rank-sum data set. So let me take a look at it again. Again, we're working with a new data set. If I go over here to the variables window, it looks like we have 3 different variables, one which denotes the group that people are in, and then an expression variable, and then an expression2 variable. So I can go to my data browser, and if I scroll down, it looks like we have 29 different patients. Looks like 15 of them are in group 0, and then the other 14 are in group 1, and then there's this expression thing and an expression 2. So for the purposes of this analysis, we're only interested in the expression, not in expression 2. Okay, so this is we're interested in comparing patients with multiple sclerosis and healthy controls in terms of expression of an immune marker. So this result here in the second column, expression, is a certain immune marker which is important in MS, and we want to see whether patients with MS differ from healthy controls. Okay? But you'll note an important difference from our previous example is that these are not matched pairs, right? We didn't find someone with MS and then measure their expression level and then match them, age and gender matching, to a healthy control for whom we then also measured the immune marker. Instead, we just got independent samples here. Okay, so that's a key difference between what we're doing here and what we did in the previous example. Previously, we had a dependent sample. Now we have independent samples. Okay, and so the reason for the difference is the previous example had matched pairs and this one does not. Okay, so hopefully that's clear. Okay, and so we showed the histogram in lecture and it didn't look very normal. So since we're unwilling to assume underlying normality, we're going to use a nonparametric test called the Wilcoxon Rank-Sum. The Wilcoxon Rank-Sum is appropriate for independent samples as we have here. Okay, so again, we could have used a two-sample t-test if we were willing to assume normality, but here in this case we are not. So we're proceeding with the nonparametric equivalent of a two-sample t-test, which is called the Wilcoxon Rank-Sum test. Okay? All right. Okay, so, and it turns out the group variable is equal to 0 for healthy controls and 1 for patients with MS. Okay? So we can carry out our first 3 steps of our 7 steps of hypothesis testing without doing any analyses at first. So our null hypothesis in this case is that remember we're now looking at the rank-sum test, so the null hypothesis is that the distribution of the expression level is the same in the MS group as it is in the healthy controls. Okay? And if we assume that they have the same shape, the distributions have the same shape, then this simplifies to the familiar question of whether the median expression level in patients with MS is equal to the median expression level in the healthy controls. Okay, so just a small point to remember: the rank-sum test, the Wilcoxon Rank-Sum test, the real null hypothesis involves the distributions, but if we assume the distributions have the same shape, then it simplifies to a test of the medians. Okay. So in step 2 of our hypothesis testing, we want to talk about the type of data that we have. So here it turns out that we have a continuous outcome and a dichotomous predictor, right? The continuous outcome is the expression level, and the dichotomous predictor is which group do you belong to? Are you a patient with MS or are you a healthy control? Okay? And in step 3, we determine our appropriate statistical test, which is the Wilcoxon Rank-Sum test. Okay? And again, we could have used a two-sample t-test if we were willing to assume underlying normality, but here we're not willing to make that assumption, so we choose the Wilcoxon Rank-Sum test. Okay, so the command we need to type into stata, not surprisingly, is rank-sum. But the rest of the syntax is a bit confusing, so I'm going to type rank-sum with no space in between. Then I type in my outcome variable, which in this example is this variable called expression, EXPR. And then I'm going to type comma by parentheses group. Remember, group tells us whether the patient has MS or is a healthy control. And then this command called porter, and I'll hit enter. And now you'll see some interesting results come from stata. Okay, so this will look very similar to what we had before. So up here we have group 0 and group 1, and it looks like we have 15 in one group and 14 in another, as we saw when we looked at the data browser. Then the rank sum in group 0 and the observed rank sum in group 1. and what we would have expected in the two groups. Again, remember that the expected column here isn't, the two numbers in the expected column aren't the same because we have 15 observations in one group and 14 in the other. If these were both 15 or both 14, then the expected sum of ranks in the two groups would be the same. They only differ here because we have one more patient in group 0 than we have in group 1. Okay? So hopefully that's clear. But again, this middle column is where the action is. That's the observed rank sum in the two groups. Okay? So the variance that stata uses is here, under adjusted variance. We presented the formula for that in lecture, but luckily it's not something we have to worry about. Stata will take care of it for us. And then here we have our p-value, which is 0.0402. Okay, this is a two-sided p-value again, and the reason I know that is because it's talking about the absolute value of z, so that tells me it's a two-sided p-value. And then finally, down here, we have a measure of the direction of the effect. So this is a cool piece of output that stata provides. So what is this saying? It's saying the probability that the expression in group 0 is greater than the expression in group 1, the probability of that is 0.276. Okay? So that's a very, very cool piece of outcome, right? Because if the two groups were equal, then the probability of one group being greater than the other group would be half, right? 0.5. But since 0.276 is less than 0.5, we know that the measure in group 1 is higher than the measure in group 0. Okay? So you see how I interpreted that. This is telling me the probability that the expression in group 0 is greater than the expression in group 1 is 0.276. Since that's less than 0.5, that tells me that the expression in group 1 is usually higher. Okay? All right. So with this information, we can complete the remaining steps of our hypothesis testing. Okay? So the fourth step is to state the summary statistics. And remember, the summary statistic is the sum of ranks in the smaller group. So here, the observed sum of ranks. So in this case, it would be the observed sum of ranks in group 0, which is 178. Then in the fifth step, we want to state our p-value, which is down here, 0.0402. Then in the sixth step of hypothesis testing, we want to compare our p-value, 0.04, to our alpha level of 0.05. Turns out that 0.04 is less than 0.05, so we decide to reject the null hypothesis. And finally, in the seventh and final step, we reach our conclusion. So we say that based on our sample, that's always an important thing to say, because remember, if you would have gotten a different sample, you might have reached a different conclusion. So we say that based on our sample, there is a statistically significant difference between the groups. And we don't want to stop there. We want to say we conclude that the expression in the MS patients is higher than the expression in the healthy controls. And the reason I knew that is because of the way this variable is coded, okay? So you have to always remember how you've coded your variables. In this particular example, 0 meant healthy control, 1 meant patient with multiple sclerosis or MS, okay? So 1 was the MS patients, and we knew from this probability statement here that the people with group equals 1, in other words, the patients with MS, had higher expression levels than the healthy controls. And so that is why our conclusion is that the median expression in the MS group is higher than the median expression in the healthy controls. Okay? So again, how would we do this if we didn't know the rank-sum command and we're just starting out with stata, so there's no reason for us to know it? We would use the drop-down menus again. So here I would go to Statistics, summaries, tables, and tests, non-parametric tests of hypotheses, so far the same place we went to for the signed rank test, but now instead of signed rank test, I'm going to choose the Wilcoxon Rank-Sum test. If I click on that, again, I'm presented with another window which asks me for a variable as well as a grouping variable. Okay, so my variable of interest is expression, and my grouping variable is called group. Then I can click on this thing that asks me, do you want to display an estimate of the probability that the variable for the first group is larger than the variable for the second group? Yes, I want that. That's that p-order command that we typed in. So if you were wondering what that was, that gives us that probability outcome. And then I'll hit OK. And you'll see I got the exact same output that, that we had gotten previously. Okay, so that's just a brief introduction to how to conduct non-parametric tests in stata. And hopefully it gives you some insight. And again, we want a big picture. We want to use non-parametric tests when we're unwilling to assume normality of our data. So when we have small data sets and then we plot our histogram and it doesn't really look normal, we can turn to non-parametric tests. Okay, so some of the lectures, I apologize, have been going long, much more than 45 minutes. So here's a case where we can stop relatively early to make up for those long lectures. Okay, so I'll stop here and I will see you in the next lecture.